This is the second Vodcast for Unit 2, and it's going to be dealing with different features that you can see on the sun's surface and how the sun interacts with the Earth's atmosphere. And there are two main objectives that you want to keep in mind while you're taking notes. First, you want to be able to describe each of the features that we discuss, whether that be on the sun's surface or in its atmosphere. And secondly, you want to be able to describe how the sun's solar wind affects us here on Earth. Alright, so first off, what does the sun look like? When you're asking that kind of question, you really need to define it better by asking how are you looking at it? Are you using different filters? And what part of the sun are you looking at? Are you looking at the photosphere? Are you looking at part of its atmosphere? So, really, let's take a look at just its surface, the photosphere, with no filters. So this is the current image of the sun, looking at its photosphere, and you can kind of see that it's a little bit grainy looking. That's that granulation we've talked about before, that in the convection zone you have the rising currents of hot, less dense plasma, and then you've got the cooler, denser parts that cause the photosphere to look like it's boiling. Right. Secondly, you see these dark regions over here and here and here. Those are known as sunspots. And that's the first little feature that we're going to be looking at. We can also look at the sun in a different form of light, known as UV, the kind of light that gives you a suntan. So here's the sun in UV light. As you can see, it looks a lot different. UV light does not look orange. This is a false color image. But the intense parts are the whiter areas where there's more UV light being emitted, and the darker regions where there's less. You can also look at not the sun's surface, but its atmosphere, just like this is just like when you are having a total solar eclipse. We are blocking out the sun's disk, and we're looking at the sun's corona. So depending on how you look at the sun and what part of the sun you look at, you get to see different images or different. So the first feature we're going to look at are the sunspots. Those are dark regions that show up on the face of the sun. They are on the surface. They are not clouds floating above it, as some used to think. And they are just darker regions. They're still pretty bright. All right. In fact, if somehow you could take them away from the sun and place them next to the full moon, they'd be much, much brighter than the full moon, but they're just not as bright as the surface of the sun. The reason why they are darker is just because they're a little bit cooler. They're up to, I think, 1,000, maybe 1,500 degrees cooler than the surrounding surface. But they're still very, very, very hot. And the reason for them being cooler, we believe, is the sun has a lot of magnetic poles where we have one magnetic north and one magnetic south. Since the sun is a plasma and it's moving in different directions, it actually has multiple north poles and multiple south poles. And the regions where the poles, the magnetic lines actually leave the surface of the sun, are where you have these sunspots. And when those exit and enter the sun, it causes the gases to be cool. They can last for several weeks. It takes about 2 weeks to see the entire sun rotate. In fact, when Galileo was first to observe these, he was able to see these evolve and disappear around the side of the sun and reappear on the other side. He could time that it takes about 2 weeks for the sun to rotate at the equator, and at the poles it takes a little bit more time. Now, if we look at a sunspot in different light, just like we did before with looking at the sun's surface in UV light, we can see that they look a little bit different. Okay, so here's a couple sunspots. Some things you may want to notice. Sunspots aren't all just black. They are dark central regions with a region surrounding them that's not quite as dark. Sometimes they form in groups. They're not perfect circles. Sometimes they're odd shapes. But this is what they look like in visible light, the light that your eyes can detect. And we look at different wavelengths. We notice that, say in UV light here, the intense part of the UV light of the sun is also where we find sunspots. And then again, keep an eye on where those sunspots occur. And then you can see at a different temperature. Again, that's where the sun is being active. It's very hot in those regions. Maybe not on the surface, but maybe above in the atmosphere. Same thing with X-ray. Now, sunspots themselves really don't affect the Earth. All right, but what they are indicators of activity on the sun. Where we find sunspots means somewhere in the sun, maybe in its atmosphere, in the corona or the chromosphere, the sun is becoming active. And if there's an increase in solar activity, there may be something known as a solar storm. Now, a week or two ago, we had a solar storm here. It really didn't affect us that much, but they can have a significant impact on our technology. Now, do we always have the same number of sunspots? Let's take a look at a time-lapse video of the sun. All right, so this first image is from 1996, and you can see there are very few sunspots. Sunspots will show up as really bright areas. There's one or two. Jumping ahead for another year, 1997, there's 1, 2, maybe some over here. Not a lot of activity. And you can see in 98, there's more. It's becoming more active. In 99, even more, and you can kind of look and see that there seems to be these loops. All right, we'll zoom in on those a little bit later, but again, those are magnetic field lines coming in or out of the sun. 2000, activity is ramping up more and more. In 2001, again, even more activity on the sun. So there's not always the same number of sunspots. And the question is then, is there a pattern to the amount of sunspot we have, or is it just a random change of events? So let's get back to looking at the different features. This is an image of the sun where you can see the surface. You can also see parts of the atmosphere using a hydrogen alpha filter. But let's look at the first feature that kind of stands out, these big flares coming off the surface of the sun. All right, a flare is basically just a large explosion off the surface of the sun. And let's take a couple close-ups. All right, so this is in a slightly different wavelength, but you can see where you have sunspots, you have these large flares, and you can see material shooting off the surface of the sun throughout the entire time. There's a big one. There's another. And again, you can see these loops. You can see that the flares have to do with these loops, which again are associated with sunspots. And if we take a little bit closer look at these things, we can see material just flying off the sun's surface. Again, those are solar flares. Now, really big explosions or large flares are sometimes known as coronal mass ejections, CMEs. These are the largest type of explosions. And again, during a solar storm, if these CMEs or these flares are pointed at the Earth, they can send material from the sun, charged particles like protons and electrons, and they can actually interfere with our power lines. They can overcharge them. They can interfere with satellites, and if nothing else, they can give us some really nice auroras. So this one's a little bit further out. Again, you can see material blowing off the sun all the time in different directions. You can see the stars in the background. There'll be a few other things like a planet and a comet in this one. but all this material is flying off into space. You were seeing that solar wind that we've discussed in the past. The large explosions are known as, again, coronal mass ejections. You can see a planet here, and there was just a comet. And then the last feature I'm going to point out here is this big arc up here. These flares that follow magnetic poles or magnetic lines back into the sun are known as prominences. They're very large arcs of gas that occur in the chromosphere of the sun. So as this stuff is flying off the sun's surface out into space, right, that is known as the solar wind. It's a bunch of ions. Again, ions are charged particles moving through space at very high velocities. Now eventually that stuff does reach the Earth, and luckily we have our magnetic field. Our magnetic field protects us from most of that material. It deflects it away from the equator towards the poles, and as it follows the magnetic lines, kind of like a bar magnet, at the poles where it's weakest, it will interact with our atmosphere. And when it does interact with our atmosphere, it causes the northern lights, known as the aurora borealis. In the southern hemisphere, they have the exact same thing, the southern lights, known as aurora australis. When this stuff actually hits our atmosphere, it's a region in space called the Van Allen belt. And as this stuff interacts with our atmosphere, it'll give us, again, those northern lights. So this top diagram here is showing the solar winds, showing it interacting with our atmosphere, our magnetic field, and hitting towards the poles, giving us these different northern and southern lights.